Okay, so I guess the slide is visible. Is the
Yes,
slide
sir.
visible? Yeah,
Yes,
yeah.
yes,
Okay.
sir.
Yes, sir.
All right. Okay, okay. So let us quickly start. Sorry, there was an internet problem in there is it's raining here and then that caused the problem. So okay, so we already studied the positional number system, which is based on radix. So you can have a base b, and you represent every number by a set of digits starting from the MSB to LSB, a minus 1 up to a minus p, with the corresponding weights b to the power m up to b to the power minus p. And we studied simple operations on this representation in the form of addition, and we build a circuit for that. So now let's take another operation which is slightly interesting and which is pretty useful. So first let us consider, so this operation is the complementation operation. So let us consider first the complementation of a single digit. So suppose you have a digit A, you know that digits in a particular base system can vary from 0 to, if the base is B, B minus 1. So the complement of a digit, let's denote by of a digit A, let's denote by A prime in some base B. So A prime base B is B minus 1, again base B minus A, B minus 1 minus A. So if base is, let's say if base is 2, then A prime is A2 prime, let's say, is 1 minus A2. So if A2 is 0, A2 prime is 1. If A2 is 1, A2 prime is 0. So you see, so basically it is nothing. You take the biggest digit, you take the largest digit that you can have in a particular base system and subtract the current digit from that. And subtract, you take the largest digit and subtract the current digit from that. So in binary, the largest digit is 1. So you subtract the current digit, you get it to 0 if the current digit is 1 and 1 otherwise if it is 0. So you see, for the case of binary, the transformation of or the operation of taking a complementation just flips the digit. 1 becomes 0 and 0 becomes 1. You can also define complementation for decimal digits. For example, if you have a base 10, so to get the complement of a digit, you have to subtract from 9, b minus 1. So the complementation of 0 is 9 itself, of 1 is 8, 2 is 7, and so on. You have to just subtract it from 9. Similarly for octal, so any base system, so octal the base is 8, so you have to get from to get the complement of a digit, you have to subtract it from 7. Naturally, of octal you can see that complement of say 2 is 5 and so on. You have to subtract from 7. Okay, so this is clear. So this is just an definition. Definition in the sense the complement of a digit is nothing but take the highest digit in that base system and subtract this current digit from that. You get the complement of this digit. Okay, so now we'll move from complement of a single digit to complement of a multi-digit number. Let us first consider a simple scheme. Suppose you have a number n and its representation in base B is, let's say, this one. Its implementation in base B. So wait a minute. Just a sec. Just 1 minute. Anyway, let me get back. Okay, so anyway, I'll leave it. Okay, so suppose you have a number n, and it's hope you can see the pointer at least. So its representation in base b is in terms of the digit am to a naught. So it's am into b to the power n, am minus 1 into b to the power m minus 1, and so on. So what we do is, so you have m plus 1 number of digits, a naught to a. So we are trying to do a complement of an m digit number in this case. So let's do a simple operation. You know how to complement individual digits, subtract them from the largest digit possible in that base. What you do for multi-digit digits is that replace every digit by its complement. Okay, so you get another number m. So the positional weights are still the same. You have b to the power m up to b to the power m minus 1 and so on. But the digits in m, what you do is that you replace am by am prime. Replace every digit by a complement. So in binary, what this would mean? In binary, this would mean that flip every digit. Flip every digit. Okay. So you get if you flip every digit, definitely you will get a new number m. Let's see what is the value of this new number. So if the new number is m, I have replaced every digit by its complement a prime, and by definition a prime is b minus 1 minus a. So I have replaced a prime by b minus 1 minus a. So it is b minus 1 minus am to the power bm, b minus 1 minus am minus 1 to the power bm minus 1, and so on. It's replacing every digit. So just if we do this algebra, so m becomes, you collect all the b minus 1 terms, and you have sigma 1 to m plus 1 b to the power I minus sigma 1 to 0 b to the power I minus am bm am minus 1 bm minus, which is n itself, the number itself. So you see, if you have a m plus 1 digit number in base b, so the value of m is nothing but b to the power m plus 1 minus 1, b to the power m plus 1 minus 1 minus m, n. Notice one thing, the largest number you can represent in base b is b to the power m plus 1. Okay, sorry, b to the power m plus 1 minus 1 is the largest number. So if you have a 3-digit number, the largest number you can represent is 999. So 3-digit is you can represent is 999. Okay, so it's b to the power m minus 1 minus n again. So just this operation of complementing every digit of a number, in the binary it would be flipping every digit of a number, leads to a new number m, and the property is if you add m plus n, so m is b to the power m plus 1 minus 1 minus n. If you add m plus n, you get b to the power m plus 1 minus 1. So this m is in some sense a complement of n. Complement of n because they add up to this b to the power m plus 1 minus 1. Earlier it was adding up to the highest digit possible. So this representation, this m is called a diminished radix complement of n. It's called a diminished radix complement of n. So if the radix is 2, it would be called a ones complement of n. Okay, what we can do is that we can slightly alter the value of m. So we got the diminished radix complement of n, which is m, by this process of flipping every bit. And what we do, we add 1 to m. We add 1 to m. Because earlier it was m plus m was b to the power m plus 1 minus 1 minus n. Sort of I want to remove this minus 1, I add 1 to m. So my new m is b to the power m plus 1 minus n. b to the power n plus 1 minus n. Okay, so I call that as n prime, and this is called a radix complement of n. So n prime, so how do you get the radix complement of m? There are two ways. One way is you flip every bit and then add 1 to it, and the value of that would be b is the base and m plus 1 is the number of digits used. It would be b to the power m plus 1 minus n. That's it. Okay. All right. So so this is another definition of complement that we got. So the first definition, the diminished radix definition is that you flip every bit and that's it. And the radix complement of any multi-digit number is you flip you complement every digit and then add 1 to it. In binary, it would be flip every bit and add 1 to it. And this would be called the 2's complement, whereas the diminished radix would be called the 1's complement. Okay, so now you can think of this as just some kind of, so if you look at a multi-digit number, you can say, let's say binary multi-digit number, you can look at it as a bit string. And this 2's complement is nothing but some kind of transformation on this bit stream. What's the transformation? A very simple transformation. You are flipping every bit and you are adding 1. It's a simple transformation. And this one, the number n, and its transform number n prime, the radix complement, they have some relation among themselves. They are kind of pairs. They are kind of pairs in the sense that if you add these two up, you get b to the power m plus 1. Okay, so this is and this is like they are pairs, or there is some relation between them. But you should see it as this is kind of transformation of the original, or a transformation of the original representation of the number in terms of digits in some base. Now, why is this transformation important? So this is a transformation this has kind of nice algebraic properties, ring theoretic properties. Like you take two numbers, you have heard of things called additive identity and others. You take two objects, you add them, always you get the same number. You take every pair, add them, you get the same number, the highest number b to the power m plus 1. So they are kind of, there is a ring theoretic implication of this. But why is this practically important? Okay, it is practically important for the following property. So suppose n is a m digit number, n is a m digit number, and n prime is radix complement. If you take any number p, and if you take any number p, then here is this nice property that p minus n is p plus n prime mod b to the power n, not directly. P minus n is not directly equal to p plus n prime, but p minus n equal to p plus n prime mod b to the power n. Mod meaning a mod a mod b is remainder on dividing a by b. It's the remainder on dividing a by b. So p minus n equal to p plus n prime mod b to the power m. For m digit number, it's b to the power n. So this is a very nice property. This you can easily verify. If you work this out, you will if you work this expression, the value of the number, you will easily see this. So this is a very nice. So this is as if this minus n is in some sense equivalent to this plus n prime. This minus n is in some sense equivalent to this plus n prime. Okay. So this observation of this complementation operation led the early developers of computer. So there was this thing, when computer was first developed, they found it pretty easy because they could deal with binary numbers using transistors and other things, and they were pretty happy with the binary representation. And initially they had only positive integers, unsigned numbers, and they could do all sorts of representation with these unsigned numbers. But then naturally it was you have to use signed numbers, which can be either positive or negative. And while this binary representation was enough to represent integers, there is this extra symbol plus or minus, and there were a lot of debate on how to represent this extra symbol plus or minus. Okay, and there was a series of innovations of how to represent, and I'll just briefly talk about them maybe, but it culminated in this Radix complement, or the two's complement representation, which basically stems from this property that p minus n equal to p plus n prime mod p to the power n. Let's take some example. Suppose I want to do, so suppose p is 3 to 1 in decimal and n is 1 to 3 in decimal. So I want to compute 3 to 1 minus 1 to 3. So I would get 198. So what is the n prime? N is 1, 2, 3 and minus n is minus 1, 2, 3. I want to find n prime. What is complement, tens complement of 1, 2, 3? Let's say. So tens complement of 1, 2, 3, how I would do is that I will first subtract from I'll first subtract from 1, 2, 3 from 999. Okay, so I'll take every digit. So the complement of 3 is 6, complement of 2 is 7, complement of 1 is 8. So 876 is the decimal diminished radix complement of 1, 2, 3. 9 minus 3, 9 minus 2, 9 minus 8. So you 1, 2, 3, you get 876 by the transformation, and then you add 1 to 8. So you get 877 as the radix complement of 1, 2, 3. Okay, so I said instead of subtracting 1, 2, 3, I would add the radix complement. I'd add n prime. So 3t1 plus 876, I get 1198. So 3 m here is 3. You have 3 digits, and b is 10. So you have to take this 1198 mod 10 cube, which is 1000. You have to take 1198 mod 1000. You get the remainder 198, and 198 is the answer. So this is an example. Let's take another example. So I have a binary number, this 9-bit long binary number 11001 and so on, and I want to subtract another 9-bit binary number, and this is supposed to be the result. So what I do, the second operand of this subtraction, I take its 2's complement. How I take its 2 complement? I flip every bit, add 1 to it. So this thing 11000101, this is the 2's complement. Okay, so I said I now just add the 2's complement to the first number. I add the 2's complement to the first number, and I get this number. And this number, if you take mod 2 to the power 9, you will get this, which again you can check is the answer. Okay, so a alternate way of subtraction you find is that, so suppose you want to compute p minus n, you first get the 2's complement of n, which is n prime, and add. So there are 2 steps, 3 steps rather. First you have to take 2's complement. You have to add the 2's complement. You know how to add already. Add the 2's complement to the first number, and for the result you take mod b to the power n. It's not directly the result. You take mod b to the power n. Okay. So this led to, so there were this property was turned out to be very attractive. So there are, for example, there are many representations. There was a sign magnitude representation of a sign number. So the most significant bit, usually the most significant bit. So what you do, so suppose you have 8 bits at your disposal, 7 bits you use to represent the magnitude of the number, and the 8th bit you use to represent the sign of the number. So there are 2 signs, positive or negative, so 1 bit would be enough. And if that bit is set to 1, it signifies the number is a negative number. It is set to 0, it signifies it is a positive number. So this was the sign magnitude representation. And you see that there was, so these were one of the earliest thing. So what they did was, it was simple. In the computer you will have 7 bits to represent magnitude, and the most significant bit to represent the sign, and you just interpret it in that way. While you look at the string of bits, you interpret that way and get back the number. But there is a problem with that, because addition, subtraction, all these circuits become very complex. And of course, how do you represent 0? If the magnitude is all zeros, which is a value 0, you call it the sign bit, you make 1 or 0, plus 0 or minus 0. So there are two representations of 0. And then somebody suggested this ones complement. So they said that what you do is that you have the sign bit, but you flip every bits to get the one complement. Okay, so if the sign bit is 0, after suppose you will take a number n and you have a sign magnitude representation in binary form. If you want to represent minus n, what you do is you flip all the bits including the sign bit. Okay, and you get the binary ones complement representation. And this also, suppose your convention is one complement representation, and then you have to interpret it. Whenever you look at this bit string, you have to interpret it this way. The advantage with this ones complement was probably subtraction could have been substituted by addition of this complement, because you get the negative number so easily. But again, there were two representations of 0. Then von Neumann in his early, so von Neumann, you know, he first wrote a kind of a memo, a document where he outlined how to build a digital computer, and that had a lot of detail. And all the modern computers you see that document is the foundation. Everything is built on that. So IBM initially used that document to build the first set of digital computers. And von Neumann first came up with the idea that you should not use ones complement, but twos complement you should use, and it has very many such advantages. So here is a small table. The advantages I'm soon explaining. Advantages is you do no longer have a two different representation of plus 0 and minus 0. You have a single representation. So if you have a 8-bit number available, the 8th bit is still reserved for the sign. Sign is still 1 for negative, 0 for positive, but the remaining bits you can use for magnitude. But the range of numbers you can represent is minus 127 to plus 128. There are only one representation. I'll soon see how. And how to get the twos complement? It's simple. You flip all the bits, including the sign bit, and add 1 to it. So here is a simple set of representations. It's the first column. The first column are the decimal values. The second column are the binary values, unsigned binary values. The third column is the radix complement. Sometimes it's called the twos complement. Notice the apostrophe. It's after s. It's basically the ones complement. You see, you just get it by flipping bits. And the last column is the twos complement, which is you get by flipping bits and adding 1. Okay, so here is another representation of a 5-digit binary number using ones complement, binary, and twos complement. Okay, so of course we don't have the sign bits in any of them. You don't have the sign bits in any, but these are. So I think this is clear. All of you have understood that how to use this ones complement and twos complement. And what von Neumann said is that the same adder, say repel carry adder or whatever, that you use for adding two number, you can be used for subtraction. Okay, we need a slightly different logic for handling the carry, which in this case would be the borrow, slightly different logic, but the circuit is more or less the same. So what you do is that you first convert all numbers to twos complement. All signed numbers, unsigned you forget. All signed numbers you convert to twos complement. Okay, and then forget about their positive or negative. We are doing addition or subtraction. Okay, so you have to, if you have to subtract a minus, you have to compute p minus n. What you do, you replace n by n prime and compute p plus n prime. So just the subtraction circuit is enough. So nobody in our discussion will talk about subtraction circuits. We'll only talk about adder circuits. Okay, so this is the fun. By the way, I mean, there is another way of finding 2's complement. You need, which is circuit-wise equally difficult. You need not complement and then add 1. What you can do is that you start from the right. For example, pick 3. You start from the right, you start from the right. Whenever you encounter the first one, you flip all the bits to the left of it. You start from the first one, you flip all the bits to the left of it. That will also give you the 2's complement. Okay. In 1's complement, you are flipping all the bits. In 2's complement, you start from the right. The first one you encounter, that onwards to the left, you flip all the bits. Okay, this is for human, it is a simpler way. You need not flip and then one addition is saved. But for computers, it's kind of, you need to have memory. It's like a sequential circuit, just like, or not a sequential, it's a kind of it's not a parallel circuit, just like a n-bit adder. You have to memorize till when you get the first one, So the circuit is equally difficult than the simple rule of 2's complement circuit-wise. Okay, so you see this 2's complement, you can also view it as a transformation of the original bit string into a new bit string. Okay, and this is from the transformation point of view, and this transformation indeed helps you represent negative numbers so that you can replace subtraction by additions. I'm not going into details of the circuit again. We'll go into it later when we talk more details of the adders. We'll talk about how to do subtraction also. But that is the advantage of this complement representation. I would like to tell you that these 2's complement, sign magnitude, 1's complement, these are not the only representative of the signed numbers. There are many others. For example, there is an XSK representation. That means you add an integer k, and then do it. For example, if you take an XS 127 representation, then -64 would be replaced by a positive number -64 plus 127. Okay, so you have a XSK represented. That is also sometimes used. If you remember the IEEE floating point format where you have a exponent and an mantissa. So in the exponent, to represent negative exponents, you have this XSK representation. That is one way. And there are many alternates. For example, I have told that the most significant digit is often the sign bit. But sometimes this is not addressed. This was addressed for a long time, but sometimes this is not out there. For example, if you want to represent very large integers, for example, if you will see later, Google, they have a protocol known as protocol buffer, prot buff kind of thing. So they have to represent very large integers, very long integers, and they can represent these long integers by concatenating a number of bytes. And these large integers may represent some index number of web pages which are in trillions and so on. They are very large numbers, and they adopt a representation called a variable quantified representation. So the number of bytes you use to represent an integer varies. You can concatenate as you need larger integers, you go on concatenating the bytes. So if you concatenate the bytes and so on, if you take the most significant digit, if you keep on concatenating in the most significant side, it would be a problem. So they stored the sign bit in the least significant bit. And there is a little bit complex encoding called the zigzag encoding, so zigzag encoding is a more complicated version of the 2's complement encoding, where you can actually have a variable length representation of numbers. You need not work with fixed point representations. You can have variable point representations, which is indeed becoming very popular. So what I'd like to convey to you that this representing numbers is not a closed story yet. It's not a closed story yet. Depending on what operations are common, what kind of numbers you represent, how large, how small. There are many high precision scientific applications which require very small numbers to be represented. They sometimes have an alternate formulation of this. We'll come to that. So there is you can have several type of representations, and the most intelligent one depends on what your operations are and what are the hardware capabilities, what are the circuits you have to do them. Google, I'll tell you, they have built in their servers, they built specialized architecture, specialized hardware to handle such variably quantified numbers. And because of the, see, always this representation depends on the hardware or the circuit you use to manipulate them. So they indeed have a different circuit so that they can do everything very fast, do such manipulations very fast. So this is not a closed story yet. You can still innovate and come up with new representations. Okay, so one more thing is that so this operation you see is kind of if you see it as a transformation, it transforms a positive number into its negative representation and so on. There are other transformations possible. For example, what I can do is that I can shift the bits either to the left or to the right. So anybody knows what happens to the value of an binary string if we shift the bits to the left or to the right?
Multiplied or divided by 2.
Multiply or divided. You can easily verify that. Okay, so this is one view. All right. So there is another view to this. Another view to is that, see, this is, I have told, if you finally look at the bit string, this is like a different number system, a different convention, a 2's complement from a different convention. But instead of thinking of this as numbers, you can think of these bit strings as kind of codes for the original numbers that we wanted to represent. Okay, so for example, if you look at this table, this 1011 is a 2's complement code encoding for the decimal number 5. You can think of this as encoding also, not just a base conversion. You can think of this in the general sense as an encoding. So now, again, for various purposes, there were many such encodings that people deal with. So let me come up with, all right, this conversion of bases I already covered. I am not covering them. Let me come up with one of the popular encoding known as binary coded decimals or BCD. Okay, binary coded decimals or BCD. So what you do in BCD is that it is again it's a binary representation, but in a form which is slightly more readable to human. In some cases, there are other purposes also. Actually, many of the early computers, very early computers, they had, instead of a pure binary, they had a BCD representation of decimal numbers, not just the. So what you do in BCD is that, so if you have a decimal number, you pick up every digit of the decimal number and represent this by their 4-bit binary equivalent. 4-bit. Why 4-bit? Because the decimal digits can be from 0 to 9. You to represent 9 up to 8, 3 digits should be enough. To represent 9, you need 4 digits. Okay, so you to represent every digit of a decimal number, you use 4 binary bits. So for example, so if you have a single digit decimal number, it's just this binary equivalent, 4-digit binary equivalent. If you have 2-digit binary number, 2-digit decimal number, if you have a 8-bit BCD number, first 4 digits are for the unit place, next 4 digits are for the tens place of the decimal. Okay, so so if you have a number, let's say 11, its representation would be 0001 followed by 0001. Okay, so you can see that this is a bit redundant because using 4-bit, I can actually represent 16 numbers, 0 to 15, but I am only representing 0 to 9. So there is a redundancy. There is a extra packing, other information you can pack into this. So usually people sometimes pack other kind of information to represent say sign or to represent say error correction, and other such things can be packed into this redundancy. That's the purpose of this redundancy. So this is another thing I'd like to mention. People sometimes form codes which do have redundancies, and they exploit the redundancy for other purposes. Okay, so the code is this. This is the simple rule. You take every digit of decimal and represent it by a 4-digit binary. It's 4-digit binary equivalent. All right. There will be redundancy, but that's okay. So this particular, so this is actually BCD is a family of codes. It's a family of codes. This particular representation, take every digit, have this 4-digit binary. It's called the natural BCD or simple BCD, or sometimes the 8421 BCD, BCD 8421. Why BCD 8421? Because you see this 4-digit I represent, the weight of every digit is 8, the most significant 4, 2 and 1. It's the weight of every, is a binary equivalent. So it's also sometimes called the 8421 BCD. So this led people to devise other BCD or other representation of decimals still using 4-digit. In fact, sometimes the people do a slight modification. What they do, since all the computers are sort of byte oriented, everything is in chunks of bytes, 8 digits. So they represent 2 decimal digits by a byte, 2 4 bits. And this can be again 2 form. This can be a packed BCD or an unpacked BCD. You can see if you are representing 2 digits, you can have 8-bit long. You can represent up to 255. So you can but 2 digits decimal is up to 99. So you have more redundancy. You can pack more information. Either it's packed or unpacked. But other things that I'll come back to this. Come back to this. This is a big algorithm. We'll explain you. Okay. But the other representation that is possible is that I still represent decimal digits by binary digits. Let's say, so I represent a decimal digit by a sequence of bits, binary digits, x3, x2, x1, x0. And I replace every decimal digit this way. But now these x3, x2, x1, x0 have different weights w. So the value of the number, the corresponding decimal number, is sigma wi xi. Note that this is true for BCD also. So BCD, if you have 0001 and if you take a 8421 weight, it's 8 into 0, 4 into 0, 2 into 0 plus 1 into 1. So it's sigma wi xi, just as in binary to decimal conversion. So now this w you can play with. You can play with this w. Okay. So w in the natural BCD is 8421. You can take other values of w. For example, you can take 2421 as the values of w. Note that you have the same weight for 2 positions. 8421 can be the value of w. Similarly, 642 minus 3 can be the value of w. So this is like this 2421 are currency denominations, and you want to compute n, you can compute n by different weightage, different number of each of these currency denominations. Okay. Naturally, you can see in this case, for example, there is not a unique code for every number. So if you have 2421, you can represent the same number by 2 different codes. Then it need not be unique. So that is one. So that is sometimes useful, not useful. But here, for example, is it unique? You have to check if it is unique. So that is one thing you need to check depending on what weights you have. And there is one more thing. If the sum of the weights is 9, say 2421 is 9, 642 minus 3 is again 9. If the sum of the weights is 9, they are kind of self-complementing code. They are self-complementing code. We'll explain what it means. Okay. But note that depending on, we'll come back to that, what is a self-computing, but note that depending on this value of w, you can get different codes. You can get different codes. So you can choose your own set of W's. And not only this set of W, you can have other transformation to get your codes also. Okay. For example, this type of code where you use these weights in values are called weighted codes. You can have other type of unweighted codes also, where it's no longer a sigma wi xi. So here are some other examples of code. Definitely we'll come back to them when we go into error correction and other things. Here is something called a Xs3 code. Okay, and the BCD is a weighted code. The last three, Xs3 cyclic gray, we'll see how to construct these codes, are unweighted codes. It's a unweighted codes. Unweighted codes in the sense that you don't get back the decimal by so you basically don't have a set of weights which you can multiply to get back the decimals. Okay, so let's see how to get these codes. So you get the Xs3 code by just this following process. You take a decimal number, take its natural BCD code, 8421 code, add 3 to it. Just add 3 to it. You get the Xs3 code. Okay. Now, it is in the sense that self-complementing. Self-complementing means that if you take a number n, okay, if you take a number n and you take its complement, which is 9 minus n, because it's a single digit, the complement will be 9 minus n. And if you take the Xs3, if you add 3 to both, you see they add up to the highest digit, 15. So that means if you take a code of n, and if you take the code of the complement of n, they are the complement in this, they add up to the highest digit. They are the complement, they are the mutually complement. So these are called self-complementing codes. Okay. There is there are some other properties also. For example, if you look at the cyclic code, we will I'm just explaining you what these codes are. We will later go into how to constructing these codes. You see, there is another nice property that the two corresponding codes of two corresponding decimals, they differ by only 1 bit. They differ by only one of the digits, one of the bits. Okay, so that's the property. And so gray code is also a cyclic code, and 0 and 9 are adjacent, so that's why I mean, give the name cyclic to this. Okay, so these are cyclic. So we'll come back to how you compute this gray code, but I think before that, let's get back in the first place how to construct BCD codes. How to construct this BCD codes. CRM, yeah, I think CRM will take over. How to construct the BCD codes.
Okay.
So CRM, I am stopping the sharing.
Okay, yeah, sure. Yeah, okay, so
maybe CRM, you can share your screen and then
I'll do that. Yeah, so what you've seen is that this BCD is essentially this representation of numbers in base 10. Okay, BCD is essentially representation of numbers in base 10. Only thing is that the symbols that you have from 0 to 9 those are represented as binary numbers. That's why you call it binary coded decimal. So each symbol 0 to 9, those are represented in binary, as you have already seen. So that's why it is called binary coded decimal. So now let me just, yeah. So if you want to convert a given binary number to BCD, you can simply use the standard conversion algorithms that you have already studied. That is, you have already seen how you can convert numbers between bases. So you can use the same procedure to convert a given binary number to the corresponding binary coded decimal number. Okay, that is possible, but that is not so efficient. Okay, that is not so efficient because you have to divide by 10, and as you can see, we have not yet studied division. In fact, multiplication and division are more complicated operations than just addition and subtraction. So we come back to subtraction a little. I mean, after this, I'll revisit subtraction a bit. But so addition, subtraction can be done in terms of addition, basically. So we'll just look at that a little later once again. So the question is, can we do things a little simpler? Yeah. Can we do things a little more efficiently? So let us see if you yeah. So let us just consider the numbers. Let us say 0, 1, 2. So let us consider this first. So if we just consider there, so you need 4 bits, right? Up to 7 you can represent in 3 bits, but beyond that you need 4 bits. So you are aware of the representations. I'm just writing those here. Alright, so this is for the first, this is how you can represent the 9 digits. Now let us consider 10. Okay, so 10, of course, you can represent, I mean, if you represent in binary, this is the representation of 10. Alright, but if you want to represent in BCD, if you want to represent in BCD, so this is, let us say, this is binary. If you want to represent in BCD, then what you'd like is, you would like it to be 1 0, right? This is the, so what can you do about it? So what you see is that if you if you look at this, if you so suppose you add 6, let us say you add 6 to this. So what you get really is 16. And if you look at this, okay, if you look at this, I mean actually the whole thing, if you look at this is really 16. Okay, this is 16. So one way you can, get this you can convert. So you find that it works for it works for 11 also. So if you take 11, all right, if you take 11 and you add 6 to this, then you again get, basically you get 11 again. And if you take 12, then again you add 6. If you add 6, you again get 12, right? And so you can complete the exercise yourself also. Alright, so all of these you get by adding 6. So actually we stop here because our problem was really with, this part, because this is with this from 0 to 9 you don't have any problem, because the binary and the BCD representations are coincide. But here you need to transform. So here you have the transformation is basically binary plus 6. Then you get the corresponding. So these are the, if you take a 4-bit representation, these are the the remaining codes which you need to handle. Up to these binary and BCD, those are the same, and this is BCD. This is of course in 2 places. All right. So what you see is that you can get the BCD by adding 6. So this is the good thing about it is that you don't need to divide by 10. Dividing by 2 is easy, but dividing by 10 is not so easy. So you don't need to divide by 10. You just all you need to do is add 6, provided that the number is greater than 9, or so if this, then you do this, okay, then you do this. So that is how you can convert from binary to BCD. So this is okay if you are just considering 4 bits. Now, what if you have a much longer number? So we find what we'll see is that there is an interesting procedure which we can use. So there, what we see is that here we are adding 6. So just make a note of this. Yeah, just a minute, please. I'll be back. I'll be back in a minute. Yeah,
Okay, so do you have any problem regarding the lab grouping? You have any thing to say, any point to raise regarding the group formation in labs?
So like I wasn't able to find a group. Like everyone I asked has already 5 people in it. So
okay, so can you mail me your name role? You don't have any preference? You can be added to any group?
yes, I'm fine with random allocation.
You are fine with random allocation. Anybody else not finding a group? Anybody else who cannot find a group?
So I am Anirban.
You are Anirban.
Yes,
so can you please mail me? Can all of you who don't have a group yet, you mail me? And one more thing, I have circulated you a Google Doc. So by today night, say 8 p.m., you add all your names to the Google Doc. Those who can't find a group, you mail me. I'll assign you a group. But please complete the grouping by today 8 p.m. because then we'll make WBCM according to the groups, and there will be only one submission per group. So you have to create login credentials. So please do it by 8 p.m. today. Okay, thank you. Over to CRM.
Yeah. So I don't know if I minimize it. Just tell me if I am audible after I minimize it. So can you hear me?
Yes.
Okay, good.
Yes.
Yeah. What did you say?
I have a query about what should we write in the report exactly. Like just
yeah. In the report, there is a specific question, I think, for this thing. For the ripple carry adder, there is a specific question. That is, you have been asked to determine the delay of a ripple carry adder. So then you just answered that question nicely. That is the only thing you need to put in the report.
Besides that, no, I'll tell you what you have to put. You have to put your name, roll number of the entire group. Otherwise, you won't be able to tally it back. You have to put your name, roll number, and then whatever question is here, as CRM has told, you just write the answer to that, nothing else. The extra thing I add is you have to add your name and roll number.
Yeah, name and roll number you add. I mean, it is good to add that, but in WBCM that will not create any problem with.
Okay. But
yeah,
still, I think let them add it.
It's a good practice. It's a good practice to put your name.
In fact, because one more thing I would like to mention right now is that later when we have larger assignments, the responsibilities will be split across 5 persons in the group. So you also have to write who has done what part. That also you have to mention later. Or if more than one person has done a part, that also is fine. But who is primarily responsible for which part of the assignment, that also you have to write. Okay, all right.
So for this assignment, we don't have to write.
No, this assignment you don't have to. Later we have larger and more complex assignments, then you have to do.
Yeah, but you can just write your. It's a good practice to just write your name and roll number. So you just write it, and of course you have to. And you can just summarize what you have done. I mean, although the main question there is to compute the delay of a ripple carry adder. Yeah. All right. So.
But you have to explain the delay. You have to explain the delay with a diagram and other things. What is the logic? Why? How do you get to this value of the delay? You have to explain all those things.
All right then. So, yeah, regarding that PDF creation, so let me just tell you that you can you have various options. So you could create a, let us say, LibreOffice document, or you could also write in LaTeX. So of course, I would recommend writing in LaTeX, because in LaTeX you can write the formulas and all much better, which is not so well done, not so well handled if you write in, say, use LibreOffice or something like that. So, and you also get to learn how to use LaTeX. So, a lot of people are using LaTeX, and nowadays you have convenient interfaces also. For example, that Overleaf is one of those interfaces. So you don't have to,
In fact, Overleaf would be better because there are multiple students in a group who are collaborating over the internet. So Overleaf would be easier for them.
Yeah, Overleaf, of course, the free version of Overleaf allows collaboration only between two people. But even then, it is useful. Yeah. Anyway, so let us get back to this.
Hello, sir. Can we have 6% in one group?
No, five is five is
No,
anyway,
5 is the limit.
Yeah, five is, it's a bit large anyway. We normally have smaller groups, but this time there are so many students, and it is difficult for a TA to handle so many students. That's why we have kept the groups, that big. Normally we don't.
Okay, sir.
Yeah. Okay. All right.
Sir, also in the instructions, it has been said that we have to submit the dot logic files also. But as we
Yeah.
saw in the lab last class, if we name the gates, if we name the bit switches and the bit displays, the simulation doesn't work. So is it fine if we don't name?
No. Listen. You just have to understand the flow, because the logic file, you can see, you save the logic file will be fine so long as you don't do the naming. So after naming, don't save it. You save it before you do the naming. So if you save it before you do the naming, it will work. Yeah.
Okay.
Just don't save it after you have done the naming. Then it will not work.
Okay, I got it. Understood.
Yeah. All right. In fact, that is how we did it during the demonstration also. I will actually add another component to that. I'll talk about that a little later. Yeah. That is how to subtract two numbers, because you have already studied subtraction, so it will just be a very simple, modification to incorporate subtraction. So I'll discuss that also. Anyway, so let us continue with this. So what you have seen is that you are adding 6. Now this adding 6 can also be done a little differently, because so that is what we'll see here. So if you look at this part, this is the part where we are explaining how you can, this is, you are adding 6. This is the place where you're adding 6. Okay, you're adding 6. This is really 6. All right, so this is what we have shown the full table here. So this is just 12. All right, now what we can do is, instead of adding 6, so we are adding 6, if you see, we are adding 6 to 4 bits. Instead, what you can do is, if you just take 1, 1, 0, or let us see what we are doing, 1, 1, 0, 0. So we are adding 6, right? So we are adding 6 this way. So this is 6, 0, 1, 1, 0. Okay. So if you look at it, this is 0. So whatever you have, whether it is 12 or whether it is 13, it. So basically, if you add this, the result will be, and if you consider say 13, so this is 12. If you consider 13, and if you add 6 to that, then the result you get is, so what you find is that this last bit is unaffected by the addition. It is just the same as this. It is just the same. It is unaffected by the addition, and the reason is quite obvious. The reason is that this bit is 0, okay? So because this bit is 0 here, so it is unaffected by the addition. So the question is then, why to do that? Why not just, draw a line here? Sorry, one second. What did I do? I got 4 bits here. So let me just do it a little differently. I'm just, so that I can draw the line properly. Yeah, so why not just draw a line here? Similarly, I can draw the line here. I'm not drawing it here because of the alignment. So if I draw the line here, what you can see is that I don't need to add 6. I can just add 3 here and shift this bit in. Okay, so here I'm adding 3. This is 3. Alright. So that is what I'm saying. So what I'm saying is, so LSB is unaffected because the LSB of this is 0, as you have seen. This is 0. Alright. The LSB is 0. So you can just add these 3 bits. You can add 3. Alright. You can add 3, and after having added 3, you can just shift this extra bit in. So that is what we are doing here. So we are adding this 1 1 0 1 1 0 plus 0 1 1. Then we get the result 1 0 1 1, and then you just shift in this bit. So in fact this is for 12. Had it been 13, you'd have just shifted in 1. The same thing, you'd have shifted in 1 for 13. Alright. So because as you have seen, the LSB remains unaffected. So if the next bit is 0, you get 12. If the next bit is 1, you get 13. That's all. So yeah. So this this is integrated into an algorithm that we present next. It is called double-double algorithm. So that is the algorithm that we shall see next. So just follow this algorithm a bit carefully. Okay. So initially, let us say that we are going to so this is the binary part. Okay, this is the binary part. And this is the BCD part. Okay, this is the binary part, and this is the BCD part. So initially this part is all 0. Okay, so you start with all zeros actually, and this is the first step. Okay, this is the first step. So what we are doing is we are so this is the binary number 48748. This is a binary number, and we want to convert this to BCD. So after conversion, you should have BCD number over here. So let us see how we can do that. Yeah. So we're going to do bit by bit. So here actually one bit has been shifted in. Okay. This bit, the bit shown in red, this bit shown in red has been shifted in. All right. So we have shifted in the first bit. All right. Now we shift in one more bit. So this is the bit. This bit was shifted in before. So this is the bit which you are shifting in now. So you have got 1 0. So you shifted in 1, then you shifted in 0. So you got 1 0. All right. Next, we shift in this one. So what is this value? 0 1 0 1. This is 5, right? So you know that whatever you shift in next. So here it is 1. Sorry, the next bit here. Yeah, sorry. Yeah, tell me.
Sir, are you sharing something? Because I don't think we can see the screen right now.
Oh, I think the sharing might have gone.
We can see the screen, sir.
We can see the screen.
Yes, sir, we can see.
You refresh.
Then
Yes,
then I
the
guess
sharing
it's
is on. The sharing is on.
okay, sir.
Are you able to see it? Yeah. Is it okay?
Yes, sir, the rest can see. I guess it's a problem on my part.
Maybe you can just quit and rejoin. Sometimes, yeah. You can just quit and rejoin. All right. So I hope, are you able to see now?
Yes, it is visible.
All right. Okay. So let us. Okay. So now, if you look at this part, this is 5, right? This is 5. Now, if with the next shift, this 5 will become 10 or 11. In this case, it will become 11 because this bit is a 1, right? So when I shift, this 5 will be multiplied by 2, and I'm going to add this next bit. So this will become 11. But you know that 11, the binary coded decimal representation of 11 is, so that's what we're seeing here. So you have got, yeah, so what you have done is, we have not yet shifted. So yeah, so over here what we have done is we are so shift and add. So we have not yet added this. So after shifting, so rather what we, sorry, let me come again. Here we have, what you have done is you have added 3. So at this stage, you know that this number is greater than or equal to 5, right? So this number is greater than or equal to 5. So what you do is you add 3. So you have added 3 here, all right? You have added 3 here before you shifted in. You added 3 here and then you shift this. So now you find that what you have here is indeed 11, all right? This is 11, BCD of 11. So this is a crucial step. Whenever the value here is greater than or equal to 5, okay, greater than or equal to 5, if x is greater than or equal to 5, add 3. So that's what we have done. We have added 3 here, and then we shift. So after you add 3 and shift, basically what you are doing is you are adding 6, okay, because that is getting multiplied by 2. So you are adding 6. Alright, so here you got 8. The result of adding 3 to 5 is 8, and then you shift it left, so that becomes 16. And to 16 you have added this 1, so it becomes, you know, This is 16 plus 1. So in BCD it is 11. In binary you would say it is 17, but in BCD it is 11. Alright. So you have got 11 here. So this is how it works. So now the rest of it actually it just goes on like that. So again we are going to shift. So this one will get shifted now. So we have shifted in this. So this 3, it's fine. It is not greater than or equal to 5. This is 7. So again you find that 7 is greater than or equal to 5. So you know what you have to do. You got to add 3. Alright. So you add 3 to 7. And after that you're going to shift. So first we add 3 and then we shift. So this is the result of adding 3. This is the result of adding 3 because this is greater than or equal to 5. We add 3 and then we shift. So when you shift, this one comes here. Alright, this one comes here. So this is what is and the interesting part is that now this so this was 4 before, so it has become 9. Okay, and of course this is now greater than or equal to 5. So we'll have to have a correction here also. We'll have to have a correction here. And what is this value? This value is also, this is also greater than or equal to 5. So we'll have to have a correction here and we'll have to have a correction here. So that is what we are doing now. We have introduced corrections in both these places, and then we have shifted. So the next bit that we shift is 0. This is the next bit. So first we add 3 in over here and also over here, because this is also greater than or equal to 5. This is also greater than or equal to 5. You introduce the correction at both these places and then you shift. All right. So this is the resulting number. So can you do a few steps on your own now? Yeah. Can you do a few steps on your own? So what will be the next step? So in the next step you find that this is greater than or equal to 5, right? This is greater than or equal to 5. So you'll have to introduce a correction here also. So that is what has been done. So you add 3 to this. This is the result of adding 3 to this. And then you again shift. So you shift the next bit, of course. So this is the result of adding 3 and then the result of the left shift. So we are just indicating the operation here. So L shift is left shift and add 3. So these are the two operations. Just you either shift or you add 3. These are the two operations. And you add 3 whenever, whenever the number becomes greater than or equal to 5. So those are shown in red whenever the number is greater than, the BCD is greater than or equal to 5. Alright, so can you do the next step? So next step is easy because all of them are less than 5. All of these are less than 5, right? So the next step will just be a, here you have a problem. This is greater than or equal to 5. This is 8. So you have to do a correction here. So you add 3 and again you shift. So why don't you do a few more steps yourself? Why don't you do a few more steps yourself? Can you do the next step? So next step, as you can see, this one is greater than or equal to 5. This one is also greater than or equal to 5, right? So you'll have to add 3 to this, you'll have to add 3 to this, This is okay, this is just 1. So have you done that? Just do that. Add 3 to this. So you get this, the result of adding 3, and then you shift the next bit in. So this is after you have added 3 and shifted it in. So now you find that you'll have to introduce a correction here, because this is greater than or equal to 5. The others will not need any correction right now. Yeah, are you doing it? Why don't you do the next step? Hello?
Can you just do it on a piece of paper, and maybe you can take a photo and paste it here.
Yeah.
Just work out one step and paste it here. I'll share the screen.
All right. You can do one thing. You don't even have to paste it. One or two of you can just put it in the chat, because again, yeah, this is quite simple. So you can just do it on your computer and just paste it on the chat also. That I think will be easier. So
yeah, this is just text, so they can just directly type in the chat also.
Yeah, you can just yeah. Or if you want to avoid making mistakes, maybe just type it in somewhere and just copy it on. So one or two of you can just do it. Okay. So are you able to do it?
I think let us give them just try for 1 minute.
Yeah, I think one or two of you should do it. I mean, just do it. Yeah. Where is the chat? Someone can, yeah, okay, someone has done it. Good.
Preet has done it. Okay. So
yeah,
it is 0, 0.
Yeah, so it's okay. I mean, you can just I think you might have, yeah, you have added and shifted. Okay, you have shown the final result after adding and shifting. Okay, that's fine. So this is the result of adding and shifting. Okay. So now what you can see is that at this stage, so this one is greater than or equal to 5, right? This one is greater than or equal to 5. Others are okay. So in the next step, as you can see, you'll have to introduce that correction here. So this is, as you can see, almost in every step, you have at least one number which is greater than or equal to 5. So it goes on this way, right? So I think you should just, just do this step also. Someone, Preet Kumar had done it last time. So anyone else, why don't you just do the next step and paste it here? That will be a good exercise. Anyone else? Can someone just do it and paste it here? Next step. So next step, as you can see, this one is 6, so it is greater than or equal to 5. This one is greater than or equal to 5. So you'll have to add 3 here, you'll have to add 3 here, and once you have got the result, you'll have to do a shift. Okay. So someone please do it and paste it. You can, yeah. Someone please do that. It's not so difficult. Someone do it. Yeah, it shouldn't take so long, I think. Okay, Aryan has done it. So yeah, it is. So he has shifted as well. Okay, good. So let us just see. So Yeah, so the steps are, simple. So I think you get the idea. So again, if you look at this, you find that, oh my God, yeah. So you find that you need a correction here, 7, you need a correction here. So these are the two places where these are okay. You don't need any correction there. So once you introduce the correction, this is what you get. All right, this is what you get. All right, this is the result. So now what you can see is that you will need to have introduce a correction here. This is the only place where you need to introduce a correction. The others are not greater than or equal to 5. It's less than 5. So after introducing the correction, this is the result. All right, and yeah, so here, if you look at this, you'll have to introduce a correction here. You have to introduce a correction here. You'll have to introduce a correction here. So 3 places you'll have to correct. So, oh, sorry. So, yeah. This is an important point. So when after, so if you have shifted in, if you have shifted in the last bit, beyond that you don't need to correct. Yeah. So I had missed out this. So after you have shifted in the last bit, so here actually the last bit had been shifted in. After that you don't need any more correction. So you introduce, that's why these are grouped together. That's why you introduce the correction only when there is at least one more bit to be. So yes, so that's why these are grouped together. But in this case, you don't need to introduce any correction because the last bit has already been shifted in. All right. So you find that it has actually, it has actually done the conversion. All right. So this is a very interesting algorithm, and what you can also see is that this requires you to have some memory, right? So it is not a combinational circuit, so it requires some memory. So we can actually design this in the lab, but this design will have to wait a little bit until we have started with some we have started with sequential circuits. So this will have to wait a little bit, but we can design this in the lab. So yeah, so of course it's not listed in the original set of experiments, but that's all right. We can have some other experiments too. So this is how this this conversion works. All right. So of course, the next step is the proof of correctness. Okay, so we will go into the correctness in the next class. But before we go into the correctness, I just want to talk about this subtraction. So sometime back you saw that you suppose you want to have a minus b, okay, or a plus b, you know how to do. You have done it in the last lab, in fact. You know, I mean, if we just take a simple thing like a ripple carry adder. So a plus b, I mean, if we just consider 4 bits, you know how to, these are all full adders. And you just this is carry in equal to 0, and you have a 3 b3 A2, B2, A1, B1, A0, B0. So this is how you add, right? F0, 1, 2, 3, and these are all full adders. All right. This is how you add two 4-bit numbers using a ripple carry adder. Okay, this is a ripple carry adder. But now, if you want to subtract, so how do you subtract? How do you do A minus B? So A minus B, you would like to add, so A plus 2's complement of B, right? That is what you want to do. So how do you get the 2's complement? So 2's complement is bitwise complement then, or you can say followed by an increment. All right, followed by increment. So for subtraction, you want to do a bitwise complement. So how can you do a bitwise complement? That can be done quite easily using an XOR gate, right? You can use an XOR gate here. And so this is say B3, and you have a full adder here as before. So you have a full adder, and here you have A3. Then you have the next full adder. You have an XOR gate here, and you have say B2, and here you have A2, and then you have another full adder here, have an XOR gate here, and this is B1, and you have A1, and then you have another full adder here, have an XOR gate here, you have, this is A0, this is A0, alright, and then you have, let us say, this this line. So this is your well, it will not be a very straight line, but and then this goes into the carry in. This is for increment. Well, let me just say that. This is the the increment part. This is that increment part. And this is your subtraction. This is a subtraction control. And once you do that, you have you have the required output. You have the required output. These are all same full headers. And this is your sum. All right, so this is your, ripple carry. So what is this? This is, you can say, ripple carry. Adder, subtractor. This is a ripple carry adder subtractor. So it's not too difficult. You just have a complementation unit here. This is really bitwise complement, and the increment is done just by introducing a 1 into the carry in. So when you want to subtract that increment for 2's complement, for getting the 2's complement of b, you just introduce a 1 over here. So that handles the increment part. So that is how you get a ripple carry adder subtractor. So I'll just add this component to your experiment. So as you can see, you can modify. So you can see that you can modify your or this could be a new component. This could be a new component which you could call a full adder subtractor. Let us say full adder subtractor, and then you can just do the rest of the experiment with this, or you can do the rest of the realization of the ripple carry adder subtractor using this component. All right, I think that would be enough for today. So any further questions? Any questions from anyone? We'll be closing now. Yeah. Anyone having a question? Okay then. So we'll stop here today and continue tomorrow. Okay. Okay. Thank you.
Sir.
Yes.
Sir, not somebody is unnecessarily editing the sheets, sir, Google Sheets of the lab and theory, sir.
So what I'll do is that I'll send a Google form.
Yes, sir.
I'll send out a Google form. Yeah.
Okay. Yeah, you shouldn't do that. You make things a little difficult that way. Are there too many changes? If it is just 1 or 2 changes, you can change it back.
Sir, our entire group's name was gone, sir. Like we edited and it was gone.
Yeah, that's a problem with the Google Doc. You cannot keep.
Yeah, I think just correct it back. Yeah.
You do one thing. You mail me. You mail me the group composition. I'll add them.
Yes.
All right.
No, I changed it, but
what do we do?
Changes it again.
Yeah, no. Let me.
But why are you doing this? See, you are all second-year people. If you do this kind of thing, it's very. I mean, it's very childish. You don't do it. You are increasing our work. That's it. There's no point wasting time on this.
So what I would suggest is just change it back. Yeah. Don't change other people's groups' names.
Don't do. I mean, this is. You do something else. You write code or do coding. You don't waste time on this kind of thing. You do it. Otherwise, it's a lot more work for us. We have to make a Google form and do all those things. I thought that, okay, in first year, I would make a Google form. You are second year. I thought that's not necessary. Anyway, you do it. You change it back.
So just, make the necessary correction. So what we'll do is after we collect it, now is it done or some work? I mean, some grouping
Groups are
is
left.
that still is some work still pending?
Everybody has put up, or then we can download it and finalize. We'll circulate it once we have finalized. You confirm that is fine or not.
Yeah, after we have circulated it, if you have any problems, you can just let us know individually. Yeah, so please don't edit any group unnecessarily. So just complete it. If you can finish by today, say lunchtime, that will be best, because we can also complete our work after that. Okay. So please try to complete it by lunchtime today.
So I had a doubt. So could we have four people in one group?
Yeah, that is allowed.
Okay.
4 is okay, but yeah. So if you can't get 5 people, you can have 4 also. That is also okay.
Yes, sir. Because some of us have taken additional only the theory part and not the lab.
Yes,
so
yes,
we only
that's fine.
the
You
group
do it.
The theory part only, na?
Got it. You
No,
can
that
make
is
groups of
also
4 also.
that is not a problem.
In
So
fact, see,
4
it
or
is not
5.
modulo 5. So some groups will be 4 or less. It's not
Okay.
the total number is not modulo 5.
And also, sir, we only have to make groups in the theory sheet, not the lab sheet, right?
Yeah, lab also. You make it both
Both.
ways, because
we only have taken addition. Some of us only have taken additional in theory one, not the lab.
The people who have enrolled in lab will make lab groups. If you are enrolled in theory, will make theory groups.
Okay.
See, what we shall do is we'll probably combine 2 lab groups to make a theory group.
No,
So
let them be separate. CRM. So I have asked them to be okay. We can combine them also. That is fine. But let it be separate. Let them make out.
Let us just see, because that has implication on the load on the TS. That's why. So anyway, we'll take a final
We'll
call.
see. Let them make it. Then we can use this.
So first make your lab groups, and then using those lab groups, we'll form the theory groups.
No, there are some people who are not there in lab.
No, it's okay. If they're not there in lab, we'll just drop them from the theory. No problem.
Okay.
And it might be the other way around also. I don't know. Yeah. Oh, all right. Okay. So please complete it by lunchtime today. Okay. Then
that will be helpful.
Yeah. All right then.
Okay. Bye.
Yeah. Bye. I'm closing now. Okay.